Excuse me. Hello, everybody. So happy Wednesday before our spring break here. I want to go over a couple of problems with you related to section 6.6. So hopefully you got that from Mrs. Habercorn. And we're going to go over examples 1, 2, 3, or numbers 1, 2, and 3, which are solving exponential equations, solving a real life problem with some Ethiopian stew, and then finally solving logarithmic equations. And so let's go ahead and jump right in. And you can see we've got example 1. And so part A of example 1, we have 100 raised to the x equals 1/10 raised to the x minus 3. And we want to be able to solve for x algebraically. Now we could just sit here and guess and check and see what we could figure out by taking 100 to the first, 100 to the second, and then putting the same variable right here. But, excuse me, one thing you can always do is you can go back to your rules of logarithms. And the rules of logarithms state, just hold on here, I've got something happening on my computer that you probably can't see, but okay, sorry about that. And our rules of logarithms, in particular, this rule right here that says if you have the logarithm of m raised to the x, you can rewrite it as x times the logarithm of m. And so we're going to use this rule on both sides of this equation. And so what we can do is we can essentially take the logarithm of both sides. So anytime you have something equal to each other, you can take the logarithm of each of those sides, and it doesn't change the value of the equation. It's still going to be equal to each other. So the first thing I want to do when I have variables in the exponents is I want to take the logarithm of both sides. And so it's going to look something like this. All right, you can see we took the logarithm of the left side and the logarithm of the right side. Then what we want to do after we've taken the logarithm of both sides is we want to apply this rule right here to both sides of the equation. So when I apply it over here on the left side, what we end up with is x times the logarithm of 100 equals, and we'll put the x minus 3, this exponent, in parentheses, times the logarithm of 1/10. And so we end up with something that looks like that. Now, the cool thing that we can work with now is we know what the logarithm of 100 is. We can do that in our calculator. And we know what the logarithm of 1/10 is. We can do that in our calculator also. So the logarithm of 100 is just 2. So this over here becomes x times 2, or 2x. This one over here, the logarithm of 1/10 is -1. So what happens over here is you get x minus 3. This logarithm ends up being equal to -1, and you do when you type it into your calculator. And so now we have this set of things in parentheses times -1, which is -x plus 3 when I distribute this -1 to both sides. Now you can see what we have is a two-step equation. So I'm going to add x to both sides. And let me move this up a little bit here. And once I add x to both sides, we end up with 3x equals 3. Divide by 3, x equals 1. And there is your answer. So just to recap what we did, anytime you have variables in the exponents, take the logarithm of both sides, which is what I did here. Then you can apply this rule to bring the exponents out front of both logarithms, and then from there you can just use your algebra to solve. Okay? So let's take a look at B, which is another example of that. You can see I've got 2 raised to the x equals 7. And so once again, my first thing, since I have a variable in my exponent, is to take the logarithm of both sides. And so I do that, and I get log of 2 raised to the x equals the log of 7. Now once again, I want to apply this rule right here. And so that tells me to bring the x out front. So I get x times the logarithm of 2 equals the logarithm of 7. And so you can see what I have right here is I have x times the logarithm of 2. Well, the logarithm of 2, if you do that out in your calculator, is just going to be a number. But what you can do, instead of computing out and working with that decimal, is you can divide by the logarithm of 2. on both sides, logarithm of 2. And now what you have to do is, since these cancel out, what you have to do to figure out x is you do this in your calculator. The logarithm of 7 divided by the logarithm of 2, and it comes out to be about 2.81. And there is your answer. Okay? So once again, we had a variable in the exponent. We took the logarithm of both sides. We used this rule right here to bring this exponent out to the front. And then we simply did our algebra to solve it. In this case, to do the algebra, we divided both sides by the log of 2. All right, let's move on to example 2 with, ooh, look at that formula. So let's pull up my answer key here. All right, so let me read example 2. It says you're cooking alicha, I think is how you pronounce that. Alicha. It's an Ethiopian stew. When you take it off the stove, its temperature is 212 degrees Fahrenheit. The room temperature is 70 degrees Fahrenheit, and the cooling rate of the stew is R equals 0.046. Using Newton's law of cooling, which is this big formula right here. This is Newton's law of cooling, in case you didn't know that. Physics, maybe? I don't know. Using Newton's law of cooling, they want you to determine how long it'll take the the stew to cool to a serving temperature of 100 degrees. Okay? All right, so in order to do this, we need to know what all of these things are. So let's go ahead and define what T sub 0 is, T sub R, and then possibly R and T, whatever other information we have. So apologize for the dishwasher in the background if you can hear that. Hopefully you can still hear me. All right, so let's talk about T sub 0. T sub 0 is the initial temperature of the stew, so initial temp. And we know if we look back at the problem, the initial temperature of the stew is 212 degrees. So that's going to be our T sub 0, our initial temperature. Excuse me. Our T sub R is our room temperature. Okay. The room temperature, it says in the problem, is 70 degrees. Your R value is your cooling rate. And that is 0.046. Right? T, little t, okay, so this little t right here is your time. And that's what it's asking you for. So that's going to be the one variable we don't fill in is little t. Excuse me. The last thing that we need to do here is we need to figure out what the serving temperature is. And that's just regular old T. Our serving temperature, and that is 100 degrees. All right, now that we have all of those variables, we want to go ahead and plug them into this formula. So we have T, which is 100, and that's going to equal T sub 0, which is 212, minus 70, which is the room temperature, times, get a blank piece of paper in there so I can move over. All right, times E, and we're going to raise E to the, since it's the negative RT power, negative 0.046 T, and then it's going to be plus 70, which is our room temperature once again. All right, so we know at some point we've got to get this this exponent out of there. Because it has a variable in it, but we have to do some simplification first. So the first thing we want to do is we want to simplify this 212 minus 70. So we're going to have 100 equals 212 minus 70 is 142. E to the negative 0.046 T plus 70. And now we want to manipulate this equation so that we get this E raised to the negative 0.046 T all by itself, excuse me. So to do that, we need to subtract 70. And we have 30 equals 142 E to the negative 0.046 T. And now what we need to do is we need to divide by 142. And what is that when we divide that out? It's approximately 0.211 equals e to the negative 0.046 t. Now we have the e raised to the 0.046 t all by itself, which is what we want to get. And so what we now need to do is we need to take the logarithm both sides. But since we're dealing with e, we can take the natural logarithm of both sides, 0.211. And I'll take the natural log, and I'm actually going to bring this out front. Negative 0.046 t times the ln of e. Okay. I'm going to give you a little shortcut about the ln of e, and the reason we want to use the natural log whenever we have that base of e is because the ln of e equals 1. So this little piece right here, essentially, it equals 1. And so what I can do is I can just cross this little piece out and say it's 1. Okay? So now what we have is we have the natural log of 0.211 equals negative 0.046 t. And so then to solve this problem, we just divide by negative 0.046. And we end up with somewhere around 34, and I think the units are minutes. Okay, so to summarize this problem up real quick, what we did is we took this formula right here, we figured out what all of those letters mean, and we filled everything in. We then took our values for each of these variables, we substituted them in here. Here we first had to subtract this to get 142. We want to get the e, the term with the exponent variable by itself. Take away 70, divide by 142, and then we want to take the natural log of both sides and then solve it. Alright, so those were exponential functions, and we'll work on those, and we'll talk a little bit more about it on Thursday when I'm back. Let's take a look at logarithmic functions, because these are not too bad in comparison. So when we have a logarithmic function, there's going to be two types that we're going to look at. The first one is where we have two logarithms that are either together, or they are equal to each other, or something of that nature. We have two of them. Here we have two natural logarithms. Well, one thing that we know is that anytime we have two natural logarithms like this, or two logarithms that are equal to each other, that automatically implies that the stuff inside of the parentheses is going to be equal to each other also. So anytime you have two logarithms that are equal to each other, the stuff inside has to be equal also, the stuff inside the parentheses, that is. And so what you can do is, what I did right here is you can rewrite the 4x minus 7 equals the x plus 5, and now it's just a real simple algebra problem. And so I'm going to take away x from both sides, and I get 3x minus 7 equals 5. And now it's our old friend, the two-step equation. So we're going to add 7 to each side. We're going to get 3x equals 12, which then implies that x equals 4 if you divide by 3. So how's that? A little bit easier than that last stew problem. Okay. All right. What about the last one here? So for the last one, what we have here, we only have one logarithm in here. You have to go back, and what you have to do is you have to recognize that this is logarithmic form, and we have to know to write this in exponential form. So let me make that a note of that. So if we write this in exponential form, remember what we got here. We've got 2 raised to the third equals 5x minus 17, because that's our base, that's our exponent, that's what it's equal to. And now look what we got. We got 8 equals 5x minus 17. It's a two-step problem. We're going to add 17. And 25 equals 5x. And since 25 equals 5x, we could go ahead and solve this. So 5 equals x. And we're done. Okay, go ahead and go to the website, class website, and on Tuesdays, Wednesday, give those problems a whirl, and we can talk a little more and see where we're at on Thursday. Okay? All right. Thanks for watching. Bye now.